Today we are going to do section 7.2 on page 849, non-homogeneous linear equations. What is non-homogeneous? That means in the previous section we have done the homogeneous ones where the differential equation equals to 0. So it's nice and comfortable. So now we're going to make us less comfortable by making it equal to some function of x. But x only though, there's no y on that side. Okay, but otherwise everything look more or less the same. And in that case, then the one that equals to 0, we'll give it a name. We'll call it the complementary equation. It's complementary to this thing, okay? So that's the easy part, which we learned how to do in the previous section. So how are we going to solve the more difficult one where it doesn't equal to 0 anymore and equal to some function of x? The way we do it is first, we will define something called yp of x. Check out this definition, where yp of x is called a particular solution because it is a solution that contains no constants and it is a solution to this thing. Okay, so let's say we found something that does work for this. All right, so that's called particular solution. And then what we're gonna do is look at theorem 7.4. Now, theorem 7.4 states that if yp of x is some kind of particular solution to this equation that we're thinking about solving, where it doesn't equal to 0, it equals to r of x, and then we'll let c1 y1 and c2 plus c2 y2 be the solution for when it is 0. Okay, that is the complementary solution equation. Then the general solution will be given by c1 y1 plus c2 y2 plus yp of x. Okay, so we add it all together and that will be the general solution. Now to prove that, we have two directions. First, we have to prove that yx does work. Now given that will this thing work? Given that the c1 y1 and plus c2 y2 is the solution for when it's 0, and ypx is the solution for when it's not 0. Now, if that is the case, if we plug this thing in to the original equation, okay, like it says, then what we're going to get is, well, this part will become 0, right? Whereas, without the ypx, the c1 y1 and c2 y2, that will become 0. Right? See down here, it says 0. And then the ypx plugged in will become rx because it is a solution for it. So if you plug it in here, it equals r of x. So if you add them together, it does equal to r of x. So this combination by addition does work. That is, this equation, when you plug it in, does work as a solution. And so that is the first part of the proof. Now, please look at this, stare at this longer, and if you want to make sure that all the algebra works out. Okay, just stare at it until each part, and verify everything until each part is accounted for. Okay, so and then the next page is. But the question is there another solution that is this really the general solution? That is, will we find something else that's also the solution that isn't included in this part? So let's say we found something that is any solution, okay? And let's see its relationship to y. So what happens is, let's say z of x is some kind of a solution to this equation. Then what we're going to do is subtract the two. That is, we are going to subtract z by y of p. Now, when you do that, then you're going to end up, being that they both are solutions, they both equal to r of x, right? So when you subtract, they're going to be equal to 0, which means that this is a solution to the complementary equation. Now, if it is a solution to the complementary equation, then being that c1 y1 plus c2 y2 is the general solution, then these two equations has to be the same for some c1 and c2. That is, you can find some constants to make these two things equal. Being this, that is, the c1 y1 plus c2 y2 is the general solution, so all solutions has to look like that. So and if that is the case, you can rewrite it and see the z of x is equal to c1 y1 plus c2 y2 plus yp of x. So that is it's all a matter of manipulating the the variables. So please stare at this more carefully, okay? If you want to get through all the details of the algebra and some basic derivative, if you stare at it long enough, it will all come together. So and everything will be accounted for. But that is the idea, is that we to prove this thing, first we plug it in to make sure that it does work, and second we find something else, and to prove that if there's something else, it has to look like that too. So that's how the theorem is proven. So with that, example 7.11, you're supposed to verify the general equation. So what you do is you are going to take the derivative, plug it in, and see if it works out. So please do example 7.11 as part of your homework. So to apply theorem 7.4, we know that we have to come up with some kind of particular solution, that is the yp of x. Once you come up with this thing, then you can plug it in. Well, anyway, we need to come up with something like this, okay? And because if we do, and we already know, and we have already figured out what the solution to the complementary equation is, so together we'll add those two things up, and then that will be the general solution for the whole equation that is not non-homogeneous. But how are we going to come up with the yp of x? Well, we are going to do it. Okay, let's go to page 851. We're going to do it by something called the method of undetermined coefficients. In other words, we are going to guess. But it isn't just a random guess though, luckily. And how are we supposed to guess that? Well, there's a trick to it, but we will mention the trick a little later, okay? But for now, let's look at example 7.12, where we use the trick a little bit. So we're going to guess. And what are we going to guess? We're going to guess that because, let's see, why is my camera not zooming in? Not sure. Well, anyway, so we are going to guess that, give me a second. Anyway, so, well, if my camera is not zooming in, you can just look at, oh, there it is. Look at your book, okay? This is, anyway, example 7.12. We have, we're going to guess that, look at this line where it says yp of x equal to ax plus b. And that we're guessing that because the r of x, that is the thing here, is 3x. See, the equation equals 3x. So our guess will be yp of x equal to ax plus b. Now, why we guess it that way, we'll explain it in a second. For now, we're just going to guess yp of x is ax plus b, and we're going to figure out what a and b are. Now, once we figure out what those a and b are just numbers, and once we figure that out, that is a particular solution, and then we add it up to the c1 y1 and c2 y2, and that will give us the general solution. Now, the solution to the complementary equation, where the equation just equal to 0, which we can come up with very quickly, okay? That is, we did that in the previous section, and by doing the quadratic roots, in fact, to calculate the quadratic roots, just type it into some quadratic root solver. I don't even bother doing it. But anyway, that will give you this answer, the 2 lambdas right away. In this case, well, in this case, we don't even need to do that. It's obvious, right? The roots are -1 and -3 right here. So then we have this thing, and so now what? Now what we are going to do is plug in, calculate yp of x, and take the derivative, okay? That is, y prime is here, y double prime is that, and plug it into the original equation, which will give us two equations like this, based on the y value. Now, the book didn't bother writing it out, but so I will do it here. See, yp of x, our guess is ax plus b, therefore y prime of x is a, and y double prime will be 0, because a and b are constants. Now, having said that, then let's plug it in, okay? So we'll plug in y prime and y double prime into the original equation. Here's the original equation up here, okay? And then we plug it in, so it looks like that. And then if you clean it all up a little bit, it looks like this. Now notice that these two equations have a situation where the coefficients of x is 3a on one side and the other side is 3. Therefore, 3a equals to 3. The numbers is 4a plus 3b. The other side is just got nothing. So that 4a plus 3b equals to 0. At this point, you have two equations with two unknowns. And then we can normally solve for a and b. And then once you come up with the value of a and b, then you know what the particular equation is. Okay, the particular equation is then, what did we call it? Oh, ax plus b. So you have a is 1 and b equals to minus 4/3. So there's ax plus b at the end. And that is the complementary, the solution of the complementary equation. And you add it together, and that is the answer. So please do this problem, this example as part of your homework. Example 7.12. All right. And anyway, next, the example 7.13, the same thing. Okay, that is they picked a y(p) of x equal to something different. This time the answer is some kind of exponent. So given that, then please calculate what the a might be. So that's example 7.3. Please do it as part of your homework. Now, so far the book has given us the guess, or how to basically presented what the guess might be for the particular solution yp. But how are we supposed to guess it? Well, there's actually a system of the guess. Okay, let's look at page 853. There's a big old chart of how you're supposed to do the guess. Now, let's look at that. See, the first one is look at the second one. That's what we did. That is, your guess depends on r of x. What the equation equals to. If r of x is ax plus b, and then in the example we just did, then our guess will be ax plus b as well, a different one. And then our job is just to calculate what a and b are. And similarly, you can look at various other guesses. Okay, that's how you're going to be doing your homework. You will see what Rx becomes, and then follow this chart to make a proper guess. And once you've done that, then you will solve for a and b somehow, and in a simultaneous equation, and then you are good to go. Now this is the easy way of solving this kind of non-homogeneous equation. And this method doesn't always work because there's only a finite list of really specific equations here, as you can see, that this thing works. Okay, and plus it gets more and more complicated as life goes on. But what if your result doesn't look anything like this? Then so this is the easy way, and we can no longer, if that is the case, if r of x equal to something odd that isn't included in this chart, then we have to do things the hard way. So let's look at the hard way. Okay, flip the page. What is all that? Whatever. And now, before I move on, I should mention that at the bottom of page 853, it shows that when this method of undetermined coefficients doesn't work. Sometimes it just doesn't, okay? And when it doesn't work, you might have to use a trick by multiplying an x on here, but it's not gonna, we are not gonna work too hard on that, okay? And we'll just, but just bear in mind that it doesn't work. If it doesn't work, well, then we have to come up with a better trick. Well, sometimes multiplying by an x works, but at least in this homework, I haven't had to do that. So we will bear that in mind and then move on. So here's our strategy for method of undetermined coefficients. It's not really necessary, I don't think, but you can look at it if you want. And so with that, please do example 7.14 as part of your homework. Let's see, which consists of 4 problems. So you're getting 4 examples for the price of 1. So please do 7.14. Example 7.14 will show you in great detail how to use the method of undetermined coefficients. But all right, so you basically do the same thing. Okay, you mess with it and then come up with some kind of a and b, and then that's your answer. Now let's move on to the next page, where a big problem comes is, what if r of x is something that isn't within the chart, which is far more likely than being in the chart. If that is the case, we have yet another trick to pull. This trick, however, is somewhat more difficult to do because you have to do integration. And then the answer tends to be messier, but it does work. So it's just a matter of patiently getting through it. So I'm now on page 857, doing variation of parameters. Ugh. Now, for variation of parameters, what we're going to do, we will start out as always. We have a quadratic equation. This time, we're going to have to keep things simpler, we're going to keep the first coefficient as just 1, whereas the other coefficients, we'll call it P and Q. So they're both numbers. So then our equation looks a little simpler. Okay, P and Q are both constants. And then we are going to define yp of x. We're gonna call it this, okay? U of x, y1 of x, plus v of x, y2 of x. Now notice that this p, we use p to stand for particular, and the other side where p and q are constants, the two p are completely unrelated. They're kind of like two kids in your class with the same name, okay? Just because they have the same name doesn't mean they are connected in any way whatsoever. So remember that the two variables are not going to be on the same side, so it's not a big deal, I don't think. But anyway, just bear in mind that the two are not related. And I rewrote this part of the proof in a way that I think might be a little easier to explain. So here's our original equation, okay, which has C1y1 plus C2y2 as the general solution to the complementary equation. That is when Rx is 0, is replaced by 0, which is fine. And then as a result of that, what that means is if we were to plug being that this is a general solution, that means if we plug y1 in there, it will become 0. Okay, and we plug y2 in there, it will also become 0. Being that C1 and C2 can be any constant, so if we put C1 equal to 0, that means y2 is a solution, and if we put C2 equal to 0, that means y1 is a solution. The point is y1 and y2 satisfies the differential equation. For just the complementary one though, okay, that is they equal to 0. They don't equal to Rx when they plugged in. They equal to 0. All right, so next we are going to define this, like I mentioned a little earlier, that we'll define, that is, we're making this up, okay? And you might think, where did we get this? We just walk around and hope to find a solution. Differential equations are very, very tough, and a lot of solutions are found this way. You just throw stuff at it and see what sticks, basically. So we're going to make this thing up, and how do we know it will solve the equation? We don't, but we're going to force it to solve it, okay, and see what happens. That is, we're just going to do some trial and error math here. So we're defining the particular solution as ux y1x plus vx y2x, and then we're going to calculate the derivatives. And so that yp is that, y prime is that, y double prime is that, and then we'll plug it in, okay? This is the original equation, see, right here, up on top. So I rewrote it down here same way, but I write Rx in the beginning. And so you plug everything in, and you get all the way down here because you're plugging in the second derivative and the first derivative, etc. So you got quite a mess of variables there, but eventually you will get to this point. Now please see my part where I says verify. Please verify this part yourself, okay? Make sure every symbol is right, that the book didn't make a mistake. And I know it didn't because I did the verifying. I double checked every single term to make sure everything comes out properly, and it is. So, but please do that yourself too. So let's say we got to here, okay, after you do all that verifying, and so we got to here, so that's good. And then we look at it very carefully. You notice that the two things in brackets are both 0 because we mentioned it earlier, okay? That's the thing about y1 and y2. Yeah, so y1 is that value. Oh, I'm so sorry. My screen is dimming. That's why it looks so odd. Okay, now that's better. So we have, and notice that there are the stuff in the brackets down here. Where's my finger? Here it is. Okay, the stuff in the brackets down here, okay, the y1 prime and so on, two of them, they are just zeros because we mentioned that earlier, being that they are solutions to the complementary equation. So these things happen to be zero, so I replaced it with zero, but otherwise the same. So we got these, and then being that they're replaced with zero, then all we have now is this following equation, which equal to r of x, okay? And as we stated earlier, so that whole thing equals to r of x. Now, so far so good. And next, we are going to pull, so the first trick we pulled is we simply define yp of x to be that uy1 and then vy2 for no reason at all, right? And the second time, now we're going to do something else, okay? We're just going to say that it is, because we're just making up this y, and we want to force it to satisfy the differential equation. And therefore, the next thing we're going to set, here's where we are, and then this thing equals to r of x, okay, as we mentioned earlier. But we are going to set this first part, this equation, to be zero, period. Because why? Because that equation happened to show up twice. If you set it to be zero, then those two things are replaced by zero, as I have typed here. And all we have then is the second equation, which equal to r of x. So now we have two equations, this one and this one, which we write it down here. Okay, so we have two equations, and look at the equations carefully. They are both equations with u prime and v prime. And with and those are unknowns. We don't know what those are. But y1 and y2, we do know what they are. And r of x, we also know what that is, which means we can solve for it. This is two equations with two unknowns. So with that, we are able to solve for u and v. And we are able to solve for u prime and v prime, which are the derivatives, okay? So once you solve for u prime and v prime, then we'll integrate each one to find u and v, and then that will give us the particular equation, which is this thing, okay, as we have decided before. And here's the original equation, and then where c1 and y1 plus c2 y2 is the solution to the complementary equation. And then finally, we add these two things up. Did I add it up? Nope, I forgot to add it up. But anyway, so all told, then we have yp plus this, that is this stuff plus this stuff, will give us the general solution of our problem. And specifically, this part right here is how we are going to do the variation of parameters. See, I marked it by the blue line. What that means is when you have an equation of this type, you're going to calculate y prime and v prime, and then solve this simultaneous equation, and then integrate, and then write down the answer. That's about it. Okay, and to know exactly what I'm talking about, please look at the next example, which will show you exactly how to do that. But before that, your book does remind you what the Cramer's rule is. Do we really need to do the Cramer's rule? Nah, I don't think so. It's just the how to solve the 2 by 2 determinant, which is right here. Okay, they do give it to you, so feel free to use this instead of trying to solve the equations by hand. Remember what the determinant is. It's just a cross. You multiply this way and then subtract multiply the other way. If you don't remember what I'm talking about, just Google it. It'll explain it real quick. Okay. In other words, the determinant on top here is R1B2 minus R2B1. So you do that cross multiplication, then subtract. R1B2 minus R2B1. Okay, and so on. So you just plug it in, and out comes your answer. we'll skip example 7.15, but you can do it if you want to remind yourself how to do the Cramer's rule, I guess. Yeah, but I don't think it's necessary. So next, let's look at example 7.16. That is, we're going to use the method of variation of parameters. Now, for example 7.16 on page 860, let's look at the first part A. Okay, we have this particular equation to solve, and as you can see, the r of x, what it equals to is something divided by t squared, which doesn't fit into our chart. Our chart doesn't have anything like that, so we got to do things the hard way. So what we're going to do is first, we calculate the solution for the complementary equation where it equals to 0, and that gives us something like C1 ET and C2 TET. And then so we know that what y1 and y2 is those corresponding things. And we calculate what the y primes are because we're following the what? Do we need to do that? Let me see. Yeah, we do need to calculate what the y1 prime and y2 prime is because that's our solution. That's our equation right here, right? We have to calculate all the stuff, and then so y1 prime, y2 prime is required. And once we've done that, then we will solve this equation by plugging in to Cramer's formula. And then so you plug everything into Cramer's formula. There's good old Cramer's formula where you would be doing a bunch of algebra and come up with some hopefully simple answer, but it might not always be simple. So that is u prime by the time you solve these two equations right up here. Okay, and plug it into the Cramer's rule. And don't plug anything wrong either. Okay, each part has to be exactly right. So once you plug it in and do the determinant, you will figure out what u prime and v prime are. But that's not done yet, because now that you know what u prime and v prime are, you will do some integration to figure out what u and v are. And once you've done that, then you are looking pretty good. Okay, then you plug it in and you figure out what y of p is. That will be your y of p. And then, but that's not the answer yet. So then you have to copy down the original y, which is c1 y1 plus c2 y2 plus y of p. Add it all up, and that will be your answer. So that is just part A. So please do this example as part of your homework, and we will move on to the next page. And I think that's it. Yep, it is. So so for homework on page 862, please do problems 55, 57, 59, 61, 73, 77, 79, and 81. And when you're done, I want to talk about all of them. Now that you're done with homework, let's talk about them. First, problem 55. Okay, I'm doing this by the chart on page 853. This is, of course, the easier problem that we start with. And then, so yp is, according to the chart, yp, depending on the very last term, which is in this case 8, r of x is just 8. So yp will just let it equal to a constant. And then I plugged it in, and we figured out that, well, then y prime and y double prime are both 0. I plugged it in and calculated that there's only a, and a is minus 2, and you plug it in there, and that's about right. In the meantime, I also had to solve the quadratic form equation, which gave me lambda equals to 1 and minus 4/3, which I plugged it into the coefficient up here. So then the entire solution is just this, and that turns out to be the right answer. So that's always good. So that's problem 55. Next, problem 57, I think is similar. We have, now this time the r of x is e to the power minus 2x. As always, I calculate what lambda is. This time lambda is imaginary, which makes no difference to us. I just follow the chart, which gives us, in the previous section, which gives us that the solution will be c1 cosine 4x and c2 sine x. And in the meantime, yp, I followed our chart, which I assigned yp equals to ae minus 2x, following this thing. And then I took the derivatives and plugged it in, and then I was able to calculate that a equals to 1 over 20. I think I messed up a little bit here, but eventually had to dig my way out and found out that what a is, and then y of x, therefore, is equal to the the general equation over here plus the particular equation over here, and that is the right answer. So that is good. And then next, let's look at problem 59, where the r of x this time equals to some polynomial. And in the meantime, lambda is a repeated root, okay, over here, so they are the same. And so I follow the rules on page 841, which means when the root is repeated, then the two things becomes the thing itself, and then you add an x to it, okay? And then we have, so then yp, I'm following the rules on page 850, whatever. I don't even remember. But anyway, I follow the rule in that chart, which says, in this case, yp has to be ax squared plus bx plus c. I calculate the first and second derivative, plugged it in, and then lined up all the coefficients. That is, this has to be equal to r of x. Then what are the coefficients for all the x squares? I wrote that down, calculated a, then coefficients for x, then I was able to calculate b, and then c is just 0, so that's good. And then eventually I came up with what yp of is, and then what the entire solution is right here, by copying what's on top for the lambda, and then add up to the yp, and that is the complete solution. All right, and then the next problem is the same way, I think. Yeah, so the next problem 61, the same thing, except that now we're doing sine x plus cosine x, but otherwise nothing is different, okay? And I got the right answer by following the rules. And finally, problem 73, we're still doing the method of, what is this called? I can't even remember what it's called already, but it doesn't matter. I follow the method without knowing what it's called. And in case you're wondering why do I say that here, when I was doing this problem, my TV gave me an ad that says the cell phone will make, in Spanish, the cell phone will make me euforisantamente. I was like, what does that mean? And then, so I looked it up, and it means that the cell phone will make me euphoric. Really? A cell phone? I mean, are they serious? I mean, don't these ad people ever think? But anyway, so that's why that's written down there. But that has nothing to do with our math. At 73, I think we do basically the same thing. You follow the charts and write down the right guesses, figure out the coefficients, and then write down their entire answer. Okay? Yeah, and that's that. So that is the end of our easy method. And from the next two problems, we're stuck with a tough method, variation of parameters or something. Yeah, well, anyway, but tough or easy, we follow the rules and we'll get to the right answer. It's only tough not in terms of tedious, not in terms of difficult, okay? There's a difference between those two things. So here is problem 77. I did exactly what I was told. See, first I figured out what lambda is, and then I wrote down y of p with u and v in there. I calculate the two simultaneous, wrote down the two simultaneous equations, and then calculate what u prime and v prime is, follow the Cramer's rule, and come up with a solution, okay? And then eventually figured out what u is, and then did the integration and v. And then eventually, so once I have that, then I write it all out, okay? Which you still have to write it out, because y of p is defined as, remember what it is, it's u times e3x plus v times e minus 3x. So you multiply, you write all that stuff out, and then come up with this thing, and eventually write out the original answer, which is correct. Okay, and which is good. I'm always happy when I got the whole thing without messing up somehow. So that is 77, and then problem 79 is the same idea, not much worth talking about. So we have the cosecant. I will show you the whole page. Yeah, that is the entire answer. again, we calculate what y of p is with u and v in it, and then calculate the derivative, set up the simultaneous equation, follow Cramer's rule, solve for u prime, v prime, and then integrate to get u and v, and then write everything out. Okay, this is the answer is this stuff plus all this. And then I checked at the back of the book, and that is correct, which is always nice. And then the last problem, problem 81, we don't have to calculate YP. Okay, the book is feeling sorry for us and is making things easy. I mean, easier. We still got a whole page of stuff, right? But if we had to calculate Y of P, then we would have had 2 pages of stuff, which if I was designing a problem, I'd probably make the student do that. But we are spared the work, so we will take advantage of less work. So here we're already given this. Okay, that's Y of P. Therefore, all we have to do is figure out, given these 2 situations, right? Y is 0 equal to -1, y prime at 0 equal to 0, which means, and we'll plug this into this equation and into the derivative, which we have to take. And then with that, we're going to calculate C1 and C2. And then that will give us the entire answer. So you plow through all this stuff. And if you don't make a mistake, see, I didn't even make a mistake. Everything is good. So eventually I calculated what C1 and C2 are, which are 2 very inconvenient numbers. Look at that. 4/343. But anyway, so I wrote that down, and that is the right answer because I checked. But partly because we're already given Y of P, so this is easier to do and not as likely to have mistakes. However, as you can see, the differential equations are very, very difficult to do. When I say difficult, I mean there's no systematic way of solving a differential equation. So what we do is we look at each situation and try to find solution for very specific conditions that we can find solutions to. Which means that, so what we're doing right now is actually very simple, right? We're just doing some basic derivatives and basic determinants, that sort of thing. But, and while it's tedious, it's still not particularly hard, but you gotta remember, we're only dealing with very, very specific differential equations. And that's the best we can do for the moment. Okay, so we will take pride in that, and that marks the end of this section.